Shell scripting is one of those things that just seems so easy when you're first getting started. You're so effective, you can get so much done. And then you try and do something just a little bit more complicated where, there's some stakes on the line and it just blows up in your face. Well, that's exactly what we're going to look at today. I'm going to share with you a couple of shell scripts that I more or less have written that accomplish real, genuine, honest-to-goodness, useful things in my work, but contain very subtle mistakes, errors that'll blow up in my face when I deploy these tools to production. Now, it's very much the case that, like many technologies that have this particular pattern of use, some of the fault is on Shell. There are some limitations, some historical, some legacy choices that were made, and some of it is on us, not totally understanding all of the core mental models behind how the shell is designed and how it's supposed to be used. We'll cover all of those in today's session, but first, here's what we're going to do. I've picked out 5 different types of errors that I might run into my shell script, and you'll see there's some overlap in them that I want to share with you. For each one of these, I'll present you with a premise and with a script or parts of a script that you might use in order to solve a particular problem. And then we'll talk about what might be wrong in that. I'll give you a chance to try and guess if you can spot where the error might be, and I'll even give you a hint along the way. But as with all classes of bugs, what's most important is not the one specific answer to the one specific instance of this one specific bug, but instead a broader explanation and understanding and an approach that we can take by building very small prototypes of a very particular nature that'll give us the mental models and the confidence to use this extraordinarily powerful but slightly tricky tool as effectively and as efficiently as possible. I want to start by talking about spacing. This is a problem that comes up in a lot of people's shell scripts, and this seems to be just about as far as most people have an understanding of what good or safe shell scripting might look like. Just put quotes around everything and just make sure the spacing is right. Let's talk about spacing. Here's my premise. I have some particular files. And here, for the purposes of our examples, in my autorunner, I'm going to be creating these files, and I'll be creating the scripts that'll then run these files. But here I have a file that just contains the numbers from 1 to 10. And I can see what files that I have created. I can do something like I can compute the XSH32 sum, XSH32 being one of the faster hashes, or maybe even an XSH64 or XSH128 sum. I can even run a program stat, which will do the equivalent of theccall stat and tell me a lot of information about this file, when it was created, the permissions, how large it is. And I might want to put this together in terms of maybe a script that can help me with my backups. I'm always worrying. If I'm backing up some data somewhere, well, could it be the case that the backup went wrong? Could it be the case that maybe somewhere along the way something didn't get transmitted perfectly, or maybe a backup didn't trigger? And I'm always worried about that. So you know what I'm going to do? I'm going to write a shell script. And the shell script I'm going to write is just going to capture some information about some files I have. Some checksums, like an XSH32 sum, and just information about when the file was created, its permissions, and its size. And I'll store that off to the side. So if I ever have to validate or verify that my backup was correct, I can just look at the backed up data. I can look at my hash sums and say, oh, the sums match, the sizes match, the file names matches, all the other attributes match. Everything in this backup is validated as having been correctly stored. So here's my beginning script. I'll allow somebody to specify some files to the command line. And if they don't, then I'll error out. Otherwise, I'll just go and I'll sort the files, and I'll compute the different XSH32 sums, and I'll also collect any of the stat attributes from these. Now, it is important that I'm going to do the sorting of these, because you can think that if I want to compare like against like, I want to compare a backup against some information, some metadata I've captured about that backup, I need to make sure that when I regenerate this metadata, it matches to the metadata that I stored. And if there is an ordering difference here, that's going to be a problem. Because what I might end up doing is I might not end up doing just an exact check. Maybe I'll just take the hash of the metadata against the hash of what I'm going to recompute. I could do something like that. And so I want to make sure that this metadata is stored in some deterministic fashion. So that's why I'll add that sorting in there. So I'll sort this and then call these. Now, just to show you this in action, here I'll create a directory called data. I'll touch 3 files in that data directory. I'll run my hasher on that, and it'll generate my hashes file, which will look like that, and it'll generate my information file, which will look something like that. And so, along the way, I have all the pieces that I need in order to identify that this backup was done correctly. And you can see since all the files contain the same thing, well, all of the hashes will match. I'm pretty confident that this very simple 3-line shell script is good to go. I'm going to deploy it to production, and it's going to blow up in my face because there's something I haven't considered. Can you spot the error in this shell script? And I will give you a gigantic hint. Spaces. Spaces in file names, new lines in file names, weird characters in file names. What are they going to do, and is this going to behave correctly? Was that enough of a hint to catch what's going on in this shell script that might blow up in my face in production? If you said, if there happened to have been a file that I was catching these hashes on, and that file happened to have a space in its file name, or a new line, or any other white space character, this script would fail to run completely. So for example, if I had a file and its name was not ABC or XYZ, but ABC space XYZ, and I run this script, I'd start getting errors here, and I might even get duplicated lines, or I might be missing output completely. That's exactly what's wrong with this script. Now, how do we fix it? Well, I'm going to share with you one possible answer for how we fix this problem that is not, in fact, an answer for how we fix this problem. The answer to this problem is not, don't put spaces in file names. It has never, ever, ever, ever been, don't put spaces in file names. And I'll tell you why. File names are a mechanism that human beings use in order to organize the computational resources they have. Human beings oftentimes think of files as being things which are titles of like a book or a legally downloaded copy of a song or a movie. And those titles have space in their file names. They're not all lowercase. They might even have punctuation characters. For example, back in the day, we used to legally acquire movies via other means. And some of those movies, like Star Wars, Attack of the Clones, would have punctuation in their file names. And the answer has never been, don't store that in the file name, because the tools that we have are actually capable of handling file names that are written like a human being would write the title of a book or a title of a paper or a title of a movie. So we'll completely exclude that answer because we do have an approach to handle this problem, and in fact, we do have a way to think about this problem in general to eliminate all of its complexity. Well, the most immediate answer to this problem might be to make use of some of the shell constructs that we have. And as you can see, for these examples, I'm using Z shell. Every part that I'm going to show you in this example and any other examples that I show you is doable in your standard POSIX shell, your sh, ash, dash, whatever it might be, or even your bash shell. All of these are possible in any shell. I happen to particularly like Z shell. I know my way around, and it does make a couple of things a little bit shorter, a little bit terser, a little bit easier, at least for me. But in this particular case, one of the choices that we could have in order to solve this problem is to make use of constructs that are provided by our shell. For example, our shell has the ability to deal with file names that contain any arbitrary character because it has the ability to represent an array separate from a string with some kind of delimiter. And it has the ability to perform operations on that array, for example, sorting it. So instead of making use of xargs and other mechanisms like that, I might just make use of an array here. And I might just sort this. And so if I replace my hasher with this version, and I do a test with a space in the file name, everything seems to work. But as is always the case, just this one particular answer is not as interesting as the underlying question, the underlying mental model, the underlying thought process for solving this, and how we can avoid these problems in general. Here is the nature of the problem. And I know for many of you, you've heard this before. Fundamentally, when we work with the shell, we are working with unstructured streams of binary data. A lot of people say that, oh, one of the problems with the shell is you're working with unstructured streams of binary data. I wish we had an object shell, like tools like PowerShell. I am personally of the opinion that that's actually not the right approach. There's a little bit of theory behind why that might be the case. I'd encourage you to take a look at the theory behind the idea of a narrow waist. But whatever the case may be, the shell is an extraordinarily general tool. It's not fixated on any one particular runtime environment. And as a consequence of being this very general tool, where every possible executable code can come together and interchange information, it cannot privilege one particular formulation for how we structure any kind of data. In other words, if you have a Python script and you're connecting that Python script to a Go binary, and you're connecting that to a shell script, and you're connecting that to something written in C and C++, the shell will allow you to do that by having no expectations of how they pass data and leaving it up to the individual units to figure out how they want to pass data. This is in contrast to something like PowerShell, where you have the ability to make use of a common language runtime to say, okay, everything can more or less interact with objects of a particular form. The downside of that is, well, you're working with untyped streams of binary data. The upside is, this is future-proof. Because if you fixated on one particular formulation for an object shell, well, what happens if you got it wrong? What happens if you're missing attributes from that? Every possible formulation for how we can, say, auto-generate structures from definitions, any kind of interface definition language, they've always had to have a version 2, a version 3. Oh, we forgot about this in version 2. Oh, we forgot we need this particular primitive type. Oh, we originally thought we didn't have to distinguish between the different types of numbers. Now we do. We did have to distinguish between unsigned integers and integers, except that's not relevant for other types. Oh, I'll give you an example. You might say, JSON. It's so general. It's so universal. JSON doesn't even have a datetime type. Well, are you going to fixate on having a datetime type? And if you have a datetime type, will you have an interval type? If you're going to have an interval type, do you have a period type? These questions are endless. And so the shell says, look, I'm not going to bother answering any of those questions for you. I'm just going to give you the ability to pass untyped binary data. As a consequence of this, it's up to you to figure out how to understand and how to translate that. And if we think about the units that were used in the original shell script, what we were doing was we were using sort with some input. And that input was input taken as a string and passed into the sort standard in. So if I give the string ABC, Y, X, Z to sort, sort should come in, and let's actually make this new line terminated. How we're going to do this? We're going to do it like this. We're going to put some new lines in here because sort wants to have these things, new lines separated. So that's what sort says. It says, all my data comes in with new lines separating the individual entities. And let's actually make this a C string so that we have that working. Then sort says, okay, I'm going to take one line separated by a new line, and I'm going to sort those. And the problem is, when you're passing in the file names, well, you don't know for certain that those file names don't happen to include inside of them the thing that sort is making use of in order to distinguish between each of the individual entities that it wants to sort on. And so, when you take that result and you pass that further on to a program like xargs, which takes some information from the standard in, an untyped binary stream, and has assumptions of what that information looks like. Specifically, xargs says this is just some kind of white space separated text, either new lines or spaces. And I'm going to pass each individual entity to some command. Well, you can see, and let's do xargs with n1, so we have just one argument passed to each process. Well, you can see xargs says, okay, each new line was one individual entry. I'm going to pass that to XYZ, and you can see if we do something like this, does xargs think that those three Zs are together as sort does, or does it think that they're separate? Well, it thinks that they're together. Well, we can think that given all of these different formulations, and all of these different choices that are made by these tools. What we need to do anytime we're passing data from one program to another using the shell, using, I might say, what the shell is really, really good at, which is constructing complex pipelines, passing data from one process to the other without having to worry, without having to care, without having to think, oh, this one was written in Go, oh, this one was written in Python, this was written in Rust, this was written in C++. Really just allowing these to be units of computation written in whatever tool, whatever language happen to be convenient, happen to be most expedient. Well, when you're doing that, one of the things that we have to think about is, what are the two sides of this pipeline going to assume about the data and the formulation for that data? And what general conventions can we rely upon? When it comes to something like a file name, what we want is some unambiguous way to represent not one individual file name, but a collection of file names, and for each file name, how we delimit them. If we think about this problem, and we think about the nature of kind of what's going wrong when we deal with this problem, what's going wrong is we're not really taking into account all the possibilities of what a file name can contain. And so here, what we have is the case where we have a couple of different file names. Here, let's do this. Let's create a couple here. And we're doing a sort star on all of these. Let's comment this out for a moment. We're doing a sort star on all of these, and we're passing this off to xargs, and we'll just do an echo n1. And this little prototype with the xargs echo n1 is a nice, cheap little way that we can check that we're piping things correctly and we're identifying, where one of these starts and one of these ends. And so let's get that going. And here, let's actually, we want to do this. We want to do ls. We want to do find type f, and pass that to sort like this. So we have something like this. Well, one of the things that we need to think about is, how do we represent an entity and the delimiter between those entities in an unambiguous fashion? And you've all heard me talk about things like in-band and out-of-band encodings. This is a classical in-band encoding problem. We have one channel, and in that channel there's an ambiguity. Is the character that we're looking at the delimiter that distinguishes between the end of one file name and the beginning of the next file name, or is it part of the file name itself? And whenever we have an in-band encoding, we have a number of ways in which we can disambiguate this. In an in-band encoding, one of the things we can do is we can prefix the data, so we can say the next 3 bytes happen to be this thing, and then that's where that entity ends, and then the next entity begins after that, so we can do some kind of prefixing. Not that commonly used in the shell. We can do some sort of partitioning, so we can say, given the input set, these particular characters are designated delimiters and they can never appear in the data itself. And that's one of the things that we can do with file names. There's other approaches that we can take, which are quoting or escaping, and we kind of do that when we're dealing with how we pass arguments at the command line itself. And we have those options. The other option we have is to use an out-of-band mechanism, to use something where we distinguish between the structure and the data in 2 different distinct mechanisms. There's no confusion. So in general, our solution to a problem like this is either to make use of an out-of-band mechanism, and an out-of-band mechanism might be, for example, making use of mechanisms provided to you by the shell itself. So nothing stops us from, let's create, and by the way, this doesn't make too much sense here. Let's create our files. Let's do something like this. Our shell actually knows that that star means to expand all the files that it can see, and it'll do this in a way which will correctly identify that there are 4 files here. So let's take a look at that. And you'll see 5 here, but I'll show you another trick that you can do to oftentimes do this. Printf is a great shell built-in to use. One of the nice things about printf is the arguments that are passed to it. If you don't have enough formatting parameters here to supply all of the arguments that are passed, it'll just repeat this format string over and over. So a nice little quick trick that you might find in your prototypes to try and figure out what was actually passed into a script is to write something like this. And you can see here that this is just going to repeat this one string over and over for each one of the arguments here. And you can see there's 5 here, not because there was a mistake in how this did any sort of globbing or identifying the file names, but because the example script that I'm running was also included in that current directory. So we're going to also take a look at ourselves. Now, when we do this, well, we have this unambiguous out-of-band mechanism, this array, and we can use operations on this. And so here I would say there's an argument for getting to know your shell a little bit better, because it'll give you some familiarity with some of the out-of-band mechanisms, which will allow you to avoid some of the ambiguity that are present in in-band mechanisms. If you happen to use an in-band mechanism, the most common in-band mechanism to address this problem is partitioning. And in the partitioning approach, what you're going to do is you're going to say, look, I've got one channel, just that one stream of binary data, and I have to encode 2 things in that channel. 1, the data itself, the file names, and 2, the metadata, the delimiter delimiting each one of those file names. When I partition, I'm looking for some unique piece of data that cannot be confused between those 2. By default, we know that the shell, as a consequence of its historical lineage, chooses spaces, new lines, any kind of white space. And that's because back in the day, people didn't put spaces in file names because back in the day they had like 8 characters plus 3 characters for the extension. They were very limited. But we live in the modern era and we don't have to live under those same limitations. Today, we know that at least on all of the Unix systems that you use and the OS X systems that you use and the Windows systems that you use, there's at least 1 or 2 characters that cannot ever be present in a file name. Dead stop, cannot ever appear. If you happen to be a Windows user, there's way more than just these 2. But at least at the bare minimum, the greatest or the least common divisor of all of these would be file names cannot contain slashes, at least the backslash, the directory separator slash, and they cannot contain null bytes, which means every program that you use that's used as part of some larger shell pipeline, sort, xargs, find, if you dig through the text for that, for the help text for that, you'll almost always find, if it's operating on things like file names, some switch that'll allow you to specify what the separator, the delimiter would be. And it's almost always the case that they will provide you either the ability to do any arbitrary delimiter, or they'll give you the ability to specifically use a null byte. So our other possible approach, and the approach that we want to use anytime we're working with any kind of shell script that works with files, is make use of an unambiguous delimiter like a null byte. Here, we're going to find each one of these files and we're going to print a null byte separating these. And our xargs our sort program is going to have a flag -z, which understands that's being given null byte separated file names, and it's going to sort them and then generate each one of these separated by a null byte itself. Our xargs has a -0. Flag name's not always the same. That knows, oh, we're getting some file names in, or something that's separated by null bytes, probably file names, and we're going to assume that the delimiter separating these is a null byte. And with that, we can see that our shell pipeline should now just work. If we didn't use that unambiguous delimiter, then this might work in our testing, but it'll blow up in our faces in production. But rather than worry our heads off about quoting things and these, what we really should think about is this problem between in-band and out-band encodings, and really think that the shell is an environment where it makes it really easy for you to connect disparate pieces, but you have to do that in a collaborative fashion. So you really have to understand what are each one of these pieces going to be expecting. And as you design your own shell scripts, you should really very closely follow in the footsteps of the designers of programs like find, sort, and xargs. That is to say, if you're emitting some data, don't make assumptions about how that data is separated or delimited. Instead, give somebody the option, and at the very minimum, give them the option to do null delimiting. I want to share one other kind of interesting detail with you. It turns out that null bytes, at least in the shells that you might use, on the Linux computers you might use, cannot appear in 2 other interesting places. You cannot have a null byte in an environmental variable, because at least in terms of how libc thinks about environmental variables, it thinks of them as a double pointer to basically null terminated strings. And the way that your libc thinks about things like your argv is it thinks of it as a double pointer to basically null terminated strings. This assumption of null terminated strings that we get from our historical C legacy is at least stuck enough in the design of all the tools that we use that it means that we actually can, in some ways, make use of this null byte outside of just file names. If, for whatever reason, we wanted to, for example, take all the environmental variables that were passed into a program and store them in some fashion so we knew where one environmental variable ended and the other one began. Like, for example, if we had an environmental variable in a program, A, B, C, and D, E, F, right? You can think that if we wanted to store these or to pass these from one program to another, how do we actually do that? Because DEF doesn't have to be DEF. DEF could have been DEF equals XYZ equals 1, 2, 3. And is that one environmental variable, two environmental variables, three? In this out-of-band encoding that is using the shell grammar, it's very clear. It's one variable. It just happens to have equal signs in it. But if we were to just pass it to another program, we might not be clear. Well, because these things cannot include null bytes, because at least in terms of the C calls that are used in order to retrieve them, they're assuming null terminated strings, you could null byte separate these. And in a very similar sense, if you are passing arguments to some program, you're passing some flags and you wanted to store all the arguments that you passed, some other flag with some option, and then something here, and you wanted to really be clear about where one of these began and the other, because your argv is also probably going to be using some of the similar mechanisms as the environmental variable, that is to say glibc, which will have an assumption of null terminated strings. If you wanted to store these flags in some fashion, you could also probably null terminate them. What this also means is when we think about how we pass data between different units in the shell, we really should think about the three major different mechanisms for passing information between units in the shell. The environmental variables, by passing them on the command line. And previously when we've talked about this, we had an analogy to React, where environmental variables are kind of like use context in React. Flags are kind of like props in React. Well, we have that. We have the environmental variables, is standard in, and we also have the flags. One thing that we should understand is where the limitations are. The standard in is the only way for us to pass data between two different shell processes where we can pass that as raw binary data up to and including things like null bytes. And so our conclusion is fairly straightforward, which is as follows. Let's not freak out when people give us files that contain spaces. File names can contain spaces. Our conclusion is that we should be careful to ensure that the tools we connect in our scripts are collaborating. And one of the ways that we do that is make sure we are using unambiguous partitioning mechanisms if we must use in-band encodings, or make use of shell built-ins to represent collections of data using out-of-band mechanisms. And this is a problem that I see in a lot of shell scripts. People don't make use of the ability to represent arrays in shell scripts, so they have all of these problems with in-band encodings. Remember, even POSIX shell has arrays. And so really understanding that the shell is not that untamable of an environment. It's an environment which, if you have the right perspective, you can bring to this. And I think the last and most important point is understand and appreciate that the shell is about connecting different programs via untyped binary data streams. And it's your choice to understand how to interpret and how to represent those data streams in order to represent the data that you need to pass between your units.